Today, we want to get into the rest of the fundamental theorems of calculus. We're going to start by calling back to our original single variable fundamental theorem of calculus. So let's talk about the single variable calculus version of the fundamental theorem of calculus. There were two parts to the fundamental theorem of calculus back in the halcyon days of single variable calculus. We had the integral from a to b of f prime of x dx is f of b minus f of a. And we also had that capital F defined by the definite integral from c to x of f of t dt is an antiderivative of little f of x. So what we're doing with these two parts of the fundamental theorem of calculus for single variable functions, this first part says that we could use an antiderivative to calculate a definite integral. So we can calculate use an antiderivative to calculate a definite integral. So the first part of the fundamental theorem of calculus says you can use an antiderivative to calculate a definite integral. The second part of the fundamental theorem of calculus allows us to do the other one. We can use a definite integral to construct an antiderivative. That's the second part here. Use a definite integral to construct an antiderivative. This second part is useful because we know that there are some functions that do not have nice antiderivatives. They don't have antiderivatives. Some functions are not the derivative of some finite combination of elementary functions. The second part of the fundamental theorem of calculus allows us to construct an antiderivative using the definite integral. And this is good because we can calculate definite integrals with just area. So we can build an approximation of an antiderivative, even if they're in a nice one, just by calculating area. And we also found out that we can calculate area to any degree of accuracy given enough data. So, great combination. Use an antiderivative to calculate a definite integral. Use a definite integral to construct an antiderivative. Now, we didn't look at this second part very much this semester because we were less concerned about building antiderivatives or finding antiderivatives. And we wanted to look more at the structure of our first parts, where we integrate the derivative by evaluating the function at the endpoints of the interval. We integrate the derivative over a set by evaluating the function at the endpoints or the boundary of the interval. So that's kind of what we want to pull out of this. We want to pull the structure out of this first part. We integrate some derivative over a set by evaluating the function at the endpoints of the set or the boundary of the set. We're integrating, and I think last week I put up this very suspicious notation. We integrate some derivative over a set by evaluating the function at the boundary of the set. in a very hand-wavy way. Notice we wrote an integral over a set. We didn't have like a dx or a dr or a dA or a dv or any of that stuff. But when we integrate something that stands in as the derivative over, and we're integrating over a set, we evaluate the function at the boundary of the set. We did this in our fundamental theorem of calculus. The set was an interval, and the boundary of the interval was just the endpoints of the interval. So in our single variable calculus, the set was an interval. The boundary is just the endpoints. So in our single variable fundamental theorem of calculus, the set was just an interval, and the boundary of the set is the endpoints. When we upgraded this, we had to do a bunch of vector calculus stuff, but when we upgraded this to line integrals, the same kind of thing happened. The gradient was kind of like the derivative of our potential function, and the set over which we're integrating is a one-dimensional path from P to Q. So here in our fundamental theorem of calculus for line integrals, the set is a one-dimensional path and the boundary is just the starting point and the ending point. This is just a curvy version of an interval. It's a one-dimensional segment that's just all curvy. In the single variable version of things, we start at A, end at B. The only path available to us is the x-axis. In this line integral case, we start at P and end at Q following some path. And what we found out was that if we integrate a gradient field, since gradient fields are conservative, the path didn't matter, which means that all that we care about is the endpoint. So we want to see this structure. We're integrating some kind of derivative over a set by evaluating the function at the boundary of the set. I'm being a little bit casual. It was simple up here because we have a function and here's the derivative. When we originally cast this, we set this up as the function. And so this was an antiderivative, but that's the same. If f prime is the derivative of f, then f is the antiderivative of f prime. We do get a little bit fishy with this notation over here by saying the gradient is the derivative of this potential function, but it's very derivative-like. The gradient is a vector field built on the partial derivatives of the function. So it's acting as the derivative. To keep our examples small, we've been mostly working in R2, and then R2 got us into Green's theorem because we had to concern ourselves with what happens. Is there anything else we need to know? What if we have a vector field that's not a gradient field? So then we had Green's theorem, where we're not dealing with a gradient field, although it works just fine for a gradient field. So Green's theorem is the scalar curl one. Green's theorem is the scalar curl one. It follows the pattern of this fundamental theorem. It follows the structure of the fundamental theorem of calculus, but it's not generally regarded as one of the fundamental theorems of calculus. So it doesn't get into the set of 3 fundamental theorems of calculus for vector calculus. Kind of a bummer, but that's all right. So in Green's theorem, we have the integral over some sets of f dot dr where C is the boundary of a set. C is a boundary of region R with positive orientation. So C is the positively oriented boundary. I should have said that first instead of boundary positively oriented. C is the positively oriented boundary of region R. So the line integral of a vector field over a positively oriented boundary of region R is equal to the double integral over region R of the scalar curl of that vector field. So here we have a set R. We have C, this curve is the boundary of that region R. And we have this scalar curl, which is the part that's sitting in as the derivative. So here's how Green's theorem fits into this classification. We're integrating some kind of derivative over a set. In this case, that derivative, in quotes, because we're using hand-wavy language, that derivative is the scalar curl of some vector field, and the vector field is acting as the function. We're integrating this derivative over the set by evaluating the function at the boundary of the region or of the set. We can tell what's going, when we have a derivative, we can tell what's going on inside by just looking at the outside. We can tell what's going on the interior by just looking at the boundary. Question? This is where we're at. We hadn't calculated anything with Green's theorem. Friday was a holiday. But this is the structure that we want to see in the upcoming fundamental theorems of calculus, because we got two more. There are three fundamental theorems of calculus in vector calculus. The first one is the fundamental theorem of calculus for line integrals. Then we have two more, Stokes' theorem and the divergence theorem. And we want to see this kind of structure. Then we want to get into the operations and see what these integrals can tell us, see what these theorems are telling us. Keep in mind, since we know what integrals are supposed to do, that's always going to be in play. Integration is multiplication, but one of the factors is continuously variable. We started off in the single variable version with area is equal to length times width, or distance is equal to rate times time, or volume is equal to cross-sectional area multiplied by height. All just variations on multiplication, but one of the factors was continuously variable. Once we started allowing vectors to have, functions to have vector outputs, we had to change our view of multiplication, and we started using the dot product. Integral of gradient of f dot dr. How much of the gradient is going in the direction of the curve? It's really what's the result of the vector pushing us along the curve. But I've been saying it, how much of the gradient is going in, or how much of the vector field is going in the direction of the curve for so long, I don't know that I can change. I think if I worked from a script, it'd be easier, because in the space of one semester, I've completely switched the way I write the letter D. So that was kind of a struggle, but it seems to have worked. And it took less than one semester. The problem was, whenever I write like path, I can make it look like this. It doesn't loop the tall part. When I write the letter B, it doesn't loop. It doesn't loop because I draw the B just with the vertical, one vertical and then an around, right? But for P, I drop down and then go back up for some reason. I don't know why. I was taught that way. I was programmed as a kid. So first you go down, then you go back up. I'm like, oh, why did you just go up and then make the circle part? I don't know. Let's see. Q doesn't matter because you start with the circle part and then just drop it down. And then sometimes you hook it. So like B and Q are kind of the same that way. Just the one vertical, then the circle part, no problem. It's really, you're just making an O with a vertical line in 4 different places. That's all those letters are, right? There's an O with a vertical here, 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 or here. That's all you're doing. That's those 4 letters. That's the structure of those 4 letters. And if you're thinking, if I learn more math, is this the kind of stupid stuff that I'm going to be thinking about? Yes, it is. You're going to look for patterns and structure, and this is going to be your curse. So if you don't want this to happen, stop. Just keep going with engineering. Don't take any more math classes. Just build stuff that's actually useful, so you don't think about stuff that makes no sense whatsoever. So the problem is, when I write the letter P, for some reason, P is just the version of Q with the letter on the line on the other side. I can go down and then back up. And for some reason, when I'm writing P, I can trace that vertical and it doesn't loop, right? Even though I've been taught cursive, see, I can't even do a cursive P. Like with a Q, I can do the cursive. With B, cursive B is just stupid anyway. right? But for P, for some reason, if I draw it this way, I can go down, up, along the same vertical line, and the P looks nice and clean. That sentence sounds ridiculous, but that's fine. But when I write D, the way I used to write D was write the circle first, and then the vertical part of the D was always looped, even when I was trying to write like non-cursive. The vertical part of the D, which is supposed to just be a vertical line, is always looped. No matter what, I couldn't draw it where the circle and then up and then back down the same line. For some reason, down, up, no problem, same line. Up, down, can't do it, always comes out looped. So this is the kind of shit that I noticed when I was like writing notes. I'm like, oh, it's really annoying that D is always looped that way. So I said, I'm going to train myself to draw the vertical part first, because the D is just a reversed B. And the way I draw B, if the vertical line is the tall part, draw that first. So I've had to train myself to draw D backwards by doing the vertical and then the loop. One semester, I fixed the way that I draw my lowercase non-cursive letter D. But I still always say how much of the gradient is going in the direction of the curve. And I cannot fix that to say, because I want the overall result. I don't just want the direction of the curve. I want how much the curve is going that way already and how much the vector field is pushing it along. You know what I mean? That's what the dot product is telling us, not just components. Dot product of a vector and a unit vector will tell us just the component in a direction. But we don't want just the component. We want to know how much is the vector field, like, is it pushing stuff along, right? We need to know that. Any questions? Oh, wait, of course not, because I was just talking about some weird quirk of my writing. Anyway. If you find yourself, while you're writing math, thinking about how you're writing stuff, that might be a time to move on, because you're being distracted. Like if you have to focus entirely on how things are being, on what's being written, then it's like, okay, you're still trying to absorb stuff. You're still trying to understand. You're still trying to incorporate that into your thinking process. But if you're like, oh, how come I write R's this way? What if I tried writing my integrals from bottom to top instead of from top to bottom? Will they come out more consistently? Incidentally, I've tried that. It doesn't work. Just make like a skinny S. Keep it that way. But when you're thinking about how you write stuff, that means like, oh, this must mean that I'm okay with, I got a pretty good idea about what's going on with this Green's theorem business. And on a related note, I don't know if anybody does it because I've been all your communication to me is coming through the computer. But if you write all caps, that needs to stop. I realized some of you were in my class last semester, and so I would stop you from writing all caps. But if you write all caps, you are wrong for doing that. Is anybody here an architect? Yeah, that settles it. You are wrong. Do not write all caps. Math is case sensitive, right? Little f's, capital F's, they're different. If you write capital E to the X, I'm just going to start taking off points. It's E to the X, not E to the X. Don't be shouting. Calm down. I'm just kidding. Calm down never works. Don't walk up to someone who's angry and tell them to calm down. That's not how emotions work. And second of all, don't you want them to calm up? Don't you want to up the calm? Anyway, some expressions need to be multiplied by -1. That's the point. All right. Here's the most inadvisable thing to do. Without talking about flux integrals, just write some down. Because we're talking about the fundamental theorem of calculus. And we needed the second one, Stokes' theorem. The apostrophe goes after the S because the S is part of the name. Dude's name is Stokes, not Stoke. So it's not Stokes theorem, it's Stokes theorem. English is stupid. Pause for writing stuff down. This is where we find out if the way that I talk about calculus works or not. So I have not talked about what it means to integrate over S, the curl of F. I haven't talked about what the curl of F is because this is clearly not the scalar curl. Let's find out if what I do works. How come this curl F is different from the scalar curl that we had before? How can you tell just by what we've written here that we're not talking about the scalar curl of this vector field? Here's a piece of evidence. What's an operation that I'm performing on this thing called curl of F? Curl of F dot dA. That tells you right there, this curl of F must be some kind of vector because it's involved in a dot product. And we don't put scalars in our dot product. We wouldn't have written a dot if I was talking about just multiplication. Must be some kind of vector. Therefore, this curl must not be the same as the scalar curl that we were talking about before. So remember that this partial F2 with respect to X minus partial F1 with respect to Y, that was our scalar curl. This curl of this vector field is dropping out a vector. So we have cleverly called this the vector curl. There are some clues with my letter choice. So I will tell you this to make sure that the letter choice makes sense. S is some kind of surface. Here's the other way we can tell that S is some kind of surface. My dot product has a dA. A little piece of a surface is going to be an area. Small chunk of a surface is going to be an area. So S is some surface. The set over which we are integrating this vector curl is a surface. I haven't told you what the vector curl of F is, but dA needs to be some part of that surface. That's how our integration notation has worked up till this point. It would be stupid to change it now to be something else in a different situation, right? So the dx is some small piece of the interval from a to b, some small delta x that we made infinitely small. The dot dr, this dr is some tangent, some vector that's tangent to the curve, to our path. It's a piece of the curve. Piece of the curve. Dx dy, that is a small piece in a double integral. That is a small piece of our region. Usually we wrote dA, but I wanted to emphasize that this is a double integral. But that dA was some small piece of a region. So it makes sense. If I say S is some surface, we look at this dA and say, ah, that dA is some small piece of the surface. But then we have to stop and say, hold up, why is dA a vector? Well, first of all, it has to be. It's involved in a dot product. So we've got this surface. We've got some vector attached to some small piece of this surface. The next step is to think about how is this dA vector related to the surface? How can we take just one vector and relate it to a surface? How do we do that? What is this dA to this surface? That's something that we're going to have to think about. What is this dA, this vector? What is that to this surface? We know these two things. The curl of F has to be a vector. This dA has to be a vector. We're using them in a dot product. So at some point, I want to know how much of this vector field is going in or how much of this vector field is contributing to this surface, this direction on the surface. What is this one vector that we have? How is it related to this surface? Let's let that sit for a minute. Over on the other side, now remember, we cast Stokes' theorem as one of our fundamental theorems of calculus. And over here, we have a typical line integral. It would be insane for me to start using the same notation to represent something different. So over here, we have some line integral. We're integrating some vector field over some curve. So that raises a question. What is C to the surface S? How is C related to this surface S? Based on our structure. So that's another question we need to ask. What is this curve C, this one-dimensional curve to the surface S? So really what we're trying to think about is how does Stokes' theorem fit into our fundamental theorem of calculus structure? That's really what we're going for. How does Stokes' theorem fit into our fundamental theorem of calculus structure? If you've been in my class before, you can tell what 3 questions I will not be answering today. And I go, well, it's 5 minutes left. At least just put up 3 questions without even hinting at what the answer might be. Actually, I've hinted a lot, but my hints are very terrible. I know this because I'm a dungeon master, so It's like, the players will figure this puzzle out very easily. It's like, oh, no, they will not. They will overcomplicate things. So don't overcomplicate things. I'm not trying to be obscure. I want you to think about how this Stokes theorem fits into our fundamental theorem of calculus. I don't want you to worry about what's a flux integral, because you're not even supposed to know what a flux integral is. I haven't even brought that up. I'm talking about the math and the structure and the notation and what we should be looking for. I didn't talk about why this dot product, why these things were vectors. I just said, well, they're involved in a dot product, so they must be vectors. And it was like, oh, yeah, totally. So you can tell I'm not going to be answering these 3 questions. You probably predicted that I was going to do the thing. If I explain this right now, everything will make sense, but I'm not going to do that because of the time. But we don't have time for that because this was only the second part of our fundamental theorem of calculus for vector calculus. Is it just divergence theorem? That sounds terrible. This one sounds like it'd have a "the" in front of it. But anyway, divergence theorem. So here's the third of our 3 fundamental theorems of calculus for fundamental theorems of calculus for vector calculus. This is the divergence theorem, or just divergence. I think it's got to be called the divergence theorem. Anyway, I'm going to say the divergence theorem. This is divergence theorem. Immediately abandoned what I decided to do. Typical. The divergence theorem is also one of our fundamental theorem of calculus. We have the integral over some solid W of the divergence of the vector field times dV. Now this is going back to our old triple integral business. Notice that this is not a dot product. So the divergence of F must be some kind of scalar, because I'm not using a dot product. I'm just using regular product. And I'm just multiplying it by dV, which is some chunk of the solid W. But this raises the same similar 3 questions that we had in the previous problem. What is S to the solid W? We still want to know what dA, the vector, is to the surface S. And now we've got this vector field. And we want to know how the divergence theorem fits into our fundamental theorem of calculus structure. how does this fit with our fundamental theorem of calculus structure? Well, like I said, these are questions that I want you thinking about, actively thinking about, or just passively thinking about. Put the questions out there and you can't help but think about them. So either set your subconscious on this or your conscious thought to this. And we'll talk more about it tomorrow. That's it for today. I'll see y'all on tomorrow. Everybody have a good day. And thanks for playing.